just the equations. So if we get into Hooke's law for these, then this is our matrix that we're looking at, and we'll follow that through. These will get more complicated as we go. Now we're going to have a four-sided stress element, but again, that's a little ahead of where we're going to be to start out with. And then when you go to 3D, then you can have, we'll have some elements that, similar to what I was showing you earlier, that'll just mesh all over the whole top of the object. And the equations. So these are the different elements that'll get used on a 3D solid, is the tetrahedron, the hexahedron, and there's reasons for using both. And the triangles tend to be a little more conservative than if you're using a hexahedron or even just a quadrilateral, 2D four-sided square. So, we use I think I used the tetrahedron on this bracket. I mean, they're okay to use. It's not like you don't use them because they produce conservative answers, but that's just one thing you have to be aware of when you're using that shape for your 3D models, is know that it's going to probably tend to be on the conservative side, and that's okay. So if we have axis symmetric solids, right? So if we have a shape like that, we're going to create a face, do it in 2D, and then revolve it. Okay. So, and then here's our torsion. So here's your double arrows for torsion if you're putting twist on a shaft or a bar, something like that. And what this will get into is dealing with war. Oh, there we go. Right? Which would be, you can describe as maybe corkscrewing, or it's coming off axis. It's not just the twist about an axis. It's now twisting about the axis. So this will give you, define the displacement. But again, this is all mostly handled in the computer, and it's not something that we're going to have to hand calculate or do anything like that. But just, you have to be aware and know what we're dealing with. Plates are another element where, the reality is when you get to the bracket for Jeff's project, you're not going to apply a plate element to it. You're just going to 3D mesh it and go, right? But if we know and understand what some of these other things are doing, then it helps us in making sure that we can analyze the results so that we're not just buying into the results. We can say, well, we know that whatever the scenario is, that it's not quite right, and that we're approaching an approximate solution, and this isn't the answer, and we're working our way up to it and attempting to try to validate the solution so that we know what we're dealing with. And shells is the last one, but essentially it's going to be a 2D strain situation, and yes, rather prone to error, just because it's what it is. So, kind of a rather quick overview, but we'll get into the trusses and the beams pretty heavily here, and we'll start trusses on Wednesday. So, but before we get to that, we have a little bit of discussion about. So I know you don't have all of well, you should have your books, right? You guys get your books? So if we were going to, so we're gonna, I mean, normally if you would do this, you would just do 3D solid and run with it, right? But let's break it down and look at it per our, well, let's see, if I go back up to this. There it is. So here's our list, right, of what we have for options as far as dealing with our different structures, right? But if we are going to apply that to these objects, so if we were going to do the axle, what do you think we would do for the axle of this? I don't know what it is, some vehicle obviously. But if we were going to pick a truss or a beam or a solid or a plate or a shell, what do you think would be the structure that we would use to model that simplistically as opposed to 3D?
Torsion bar and shaft.
Torsion bar. So, yep, we're going to deal, well, you say shaft, torsion bar and shaft. Okay, what else though? Think about the loads that you have on it. Well, it is in a housing, I guess. And you should have bearings at each end.
Could you use the axisymmetric solid one?
Yes.
Since it does have.
I was thinking about a beam, but I was forgetting about, you've got bearings at each end, and it's, well, once you get past the bearing, out at the end that's holding the brake and the wheel itself, you could treat that as a beam. So you could, so even just this simple axle, you can model it 2 or 3 different ways to provide you with solutions that are guiding you towards the answer, right? Or for different parts of it. How about the hydraulic pressure cylinder? I mean, if we just look at the cylinder part, what would you use for the cylinder part?
Shell?
We can do a shell. Yep, absolutely. So maybe some other portion of it. I mean, the rod that goes up to the piston.
The piston could be a plate, right?
Piston could be a plate.
The end cap could be plates too.
Probably, yes, they could. Yep. And then the rod that goes in and out. How would you treat that?
Have to be a shaft.
Well, it doesn't have to be.
You could do, I mean, you can make that like a boom too, can't you?
Yeah.
Well, how are the loads on the rod?
Well, it's axial loads, right?
Typically, they're going to be axial loads, right? They're not. You don't want any bending loads on it. So if they're axial loads, you're going to treat it as a
Symmetric solid.
truss.
Oh yeah, I guess so. Okay.
Because it's an axial load, right? It's only tension or compression. You don't have any bending. It's pinned at each end, let's say. I mean, it's not pinned where it connects to the piston, but I mean, we can idealize it as that, right? Even though I guess it would resist a moment there. But I mean, when you have a hydraulic cylinder, you don't want any moments on that. You just want it going straight in and out. If you've got a moment, then it's going to be binding on the seals and mess up the cylinder. So, okay, so good. How about we got turbine disc?
Well, this is the revolving one, right?
Well, this would be, yeah.
So couldn't we just look at the one face of it?
So it'd be an axis symmetric solid. Yep, absolutely. And then, let's see, what was the next one? Oh, the turbine blade root and disc interface. Okay, so I'm guessing they're talking about this here. Or, well, maybe they mean that. I'm not sure. Because you could do this one lots of different ways too. I mean, it depends on what, what part of it you're looking at. So, well, here, since that one's a little unclear, let's try some of these. So we have a holding tank. So that one should be pretty straightforward, right?
Shell.
Shell, yeah. And let's see, gear teeth. Probably a couple different ways to do that, huh?
Three-dimensional solid.
Three-dimensional solid would be one way, you bet. Absolutely. You can treat each, if you treat the root of it as solid, then you can treat the tooth as a beam, right? May not be the best approximation, but it's feasible. Let's see, so what are they asking for on the V-belt shiv? I have no idea. I don't know what you do for that. Okay, so let's do H, because I don't know what they're asking for. I mean, you're just going to treat it as a 3D solid as that picture is showing. So what about the H?
Could you do that as a truss one?
Some of them you can, yeah. So like this link here, you could. I think you can do these. This would, well, how would you treat this one?
Well, if you assume the force was right at the end of the beam.
So yeah, you could treat this as a beam, right? So this is a truss. This is a two-force member, even though it's got an elbow in it. So we could still treat that as a truss, or we could break it up and make it a beam. So, okay. So, doesn't seem quite so scary now as far as trying to apply a structural element to what we're trying to do. Okay, so I had, so what's that? Well, I need those other guys here with their computer because I don't want to start without them. Okay, so let's do this.